Really is starting section 3.3, which is a continuation of chapter 2, where in chapter 2 we studied one-dimensional motion, motion left and right or motion up and down, whereas in this section what we're going to do is take a look at motion that's up and down and left to right, both. So think about any real-life example of an object being thrown. Any object that's literally thrown across the room has to move in 2 dimensions. Nothing will move really in 1 dimension perfectly. Even if I drop this, it kind of moved to the left a little bit when I let go of it like that. Nothing's going to fall perfectly, I mean, unless it's a perfect free fall in a closed experiment. But even if I wanted to throw this ball over to Liam, and I threw it directly at him like that, when it was coming toward Liam, the ball was descending, right? And he made that nice quick grab there. So do it again, right back. So what we notice is it looks like it's maybe linear, right? It looks like it's a line drive in a sense, you would say in baseball, but every ball really has some sort of vertical trajectory. So in this section, even objects that maybe get shot horizontally, like imagine shooting a bow and arrow. You know, when people used to hunt animals with bows and arrows, they'd have to look at the arc of the trajectory, because the arrow, after a certain distance, would start to fall over, wouldn't it? So if you want to shoot a deer or shoot an animal that's running for, some sort of, sorry for any vegetarians, but if you want to shoot something for food and you were like a hunter-gatherer, you would have to aim a little bit high, because the object would naturally, the bow itself, or the arrow itself would come out of the bow and it would descend. Remember how many people went last summer, right? Did any of you guys go last summer? Yeah, and the camp. In the bow and arrow, you always have to aim a little bit higher than where it was going to land, because if you don't shoot it off with enough velocity, it's bound to start to fall a little bit. Even if you shoot it like a speeding bullet, it still falls. You could take an actual gun, shoot a bullet perfectly horizontally. It will go a lot further than a bow and arrow or an arrow would, but eventually it would fall to the earth.
It slows down. Okay?
It slows down, and because gravity pulls it to the earth. Both those reasons. I'm guessing because of the kickback. There's kickback, and usually your target's not 1,000 yards away. If you're using like a sniper rifle and you're shooting, you actually have to account for the descent of the bullet. You have to account for the curvature of the spin and stuff. There's a lot to it. But in general, objects are going to fall down. Yeah, maybe there because it has a little kick. There's a little, what is that called, recoil? Yeah. So I'm guessing that's why. But in general, objects moving in the horizontal direction will fall vertically as well. Okay, so that's what we're going to look at here in this section. We're going to talk about the shape of parabolas as our shapes, which you're going to see in your Algebra 2 trig course, if you haven't already. And you already have, perfect. So you know what the general shape is. So the shape of a parabola is what we're going to be looking at. Stuff as well. So let's first define 2 things. A projectile is any moving object that can be modeled as a point in space. Okay, any object that could be modeled as a point in space. Projectile motion simply means 2-dimensional motion. And then notice I put, or free fall, with initial horizontal velocity component. What the heck does that even mean? Let me explain. So this is free fall, right? That's what free fall is. So that's free fall. That's not projectile motion. It's only 1-dimensional. But if I were to take this tennis ball and roll it off the table, technically speaking, it's only got velocity in the horizontal direction because it's moving left to right. So the vertical velocity is technically 0 to start. So this is actually a free fall, but a free fall with horizontal motion involved. Think about it for a sec, ready? As it's rolling, the velocity cannot be up or down because it's moving which way?
Left and right.
Left and right. So the velocity right now is only horizontal. Even when it departs the table, it's still only horizontal. Even when it's about to leave the table right here, it's still only horizontal. Then it starts to descend and picks up vertical velocity. So in this chapter, we have to differentiate between vertical velocity and horizontal velocity. That's why we did all that stuff with trig. I know, it just blew your mind. I saw that. So we're going to have to use that. The whole entire chapter, this concept of vertical and horizontal velocity.
Oh, because it makes a triangle.
And yeah, very good. That's where the trig comes into play. You see the triangle already? Okay, this is like your vertical component, horizontal, resultant. That's what we've been doing over and over again. Okay, so let's continue. So we talked about the path of a projectile. Now, what if I asked you the following? in the diagram, label one of these as real life and one of these as the simplified physics version. Which would be which and why? You have to think about it. Don't just answer right away. Which of these would be like a real life situation? Which of these would be what we consider in physics to simplify things? And why? You don't pick up on this. It's not easy to see.
Would the black one be real life and the blue one be?
Why?
Because when you simplify it, you don't account for the friction that they are causing.
That's exactly right. Very good. This is what we're going to be seeing in physics class, where it's a perfect projectile or a perfect parabola because you ignore air resistance or friction. But when you include it in real life, this is the actual path with air resistance. Okay, we should all know by now that an object moving through the air, free to move, not a jet plane in the sky or something, but an object moving freely, can only be slowed down by air resistance. If air helps it, it's not really air resistance anymore. So if like a gust of wind comes by and helps speed this up, it's not really air resistance. That's more of like a tailwind. Okay, so the actual object is pushed forward. But air resistance will slow down the object. So the shorter path takes into account air resistance. We are going to assume air resistance is 0 in this class, simply because to calculate it, we need a little more knowledge than right now when you study in math. You've got to get through a little bit of calculus before you can start including air resistance, because it involves what's called a differential. Okay, a term in calc that something that you haven't learned, and even calculus students in Mr. Linus' class are only just learning about it now. Okay, so we're going to assume in our class that there is no air resistance. So we're specifically talking about this perfect parabola here. Okay, not the one where it gets shorter because of air resistance. So let's take a look now. Okay, at this example we talked about, right, over the tennis ball a moment ago. Can I get a volunteer, or 2 volunteers actually? I'm going to need for this. I need 2 volunteers for this. Wow, Chris and Francis, come on up. Chris and Francis. All I want to do, okay, I appreciate all those that volunteered. Most people don't always volunteer as much. That was so cool. I'm actually really happy about that. Nice. All right, so here's what I want you to do. One of you needs to roll this off the desk. Okay, so we'll use this as the example. Legs for a sec. Okay, let's click the laps on here. On that side, just click the laps. Oh, is it plugged in before? It is plugged in before.
Do you want me to go?
No, it's alright. Yours is also plugged in. I plugged all these in last week for the engineering class. That one is true. The middle one is not. We go to the middle. Alright, let's figure this out. Actually, we can do it right here. We can do it right here. So what's going to happen is this. One of the 2 of them is going to roll one of these objects, maybe starting over here, and we'll roll it this way. The other person is going to drop the other object the instant this one falls off the table. So this one's going to be rolling, okay? As soon as it's about to fall off the table, when it gets to literally the surface here, like where it interacts with the edge of the surface, this other person is going to drop this ball from the same height and fall from. Does that make sense? Does that make sense? Okay? So you want to roll, do the person rolling, do the person dropping. Okay, so what you're going to do is put it on the table and just literally slide it off to the edge and we're going to drop it over here. Okay? So you could be off the table already. Go with yours, maybe in here, and go a little bit faster. And just listen. Just listen, please, carefully. Did you hear almost only one bounce land? There's a tiny difference because obviously human error or human reactions can't respond that quick. Not in general. So hold yours off a little bit. Go back. Go over time. It's a tiny little time difference. Now, theoretically, what do you think should happen?
Well, I think that the one speed in the beginning would fall down fast.
That's what you would think common sense because it has velocity, right? But as physics students, knowing that this object is only moving horizontally, and we're trying to find the time it takes to fall vertically, what do you think should happen between the 2? They should fall at the exact same time. But let's go over this one more time. Go ahead, Francis. One more time. Go a little bit faster. Go toward like right here. Okay, so your ear is almost identical right there. The reason, let me go over this. Thanks. The reason is this. When this object is falling like this, right, when this person lets go, what's the initial velocity?
0.
0, right? That's the initial vertical velocity. But we haven't been using that term. We just keep saying initial velocity. But technically, the initial vertical velocity is 0. Well, when I roll this off the table, as soon as it leaves the table, it starts to fall. It has initial horizontal velocity because it's moving. But the vertical is 0 still, because I'm not throwing it downward, right? Watch, if I do this, then I've got some initial vertical velocity, whatever that is, negative 2 meters per second. But if I just drop something, it's the equivalent of rolling something horizontally and dropping at the same time. So if I drop something, as soon as this falls off the table, it's like this one is falling vertically finally, and this one is only falling vertically. The one that's rolling off the table, though, what does it also do? It moves out from the table, because it's got horizontal velocity. So although I drop this and it takes the same time to land, the one that was rolling falls a certain distance away from the table. So that's what you're seeing here in this diagram. And there's actually a device that, like some lab, you can buy like lab supplies as science teachers, and there's a lab that they actually sell this device. And one gets shot horizontally, one gets dropped at the exact same time. And you hear that land at the same time. You have 2 tennis balls, you can demonstrate the same thing, but without as much precision, right? And it's a machine that literally does this. It literally just drops that at the exact same time the other one gets launched horizontally. And you can create apparatus to do this. You can make something so that there's a device where you push a switch, and as soon as you push the switch, it launches something, maybe from a spring-loaded mechanism, and while that's happening at the exact same time, a little gate opens up, and the other object drops. So they both go off at the same exact time. But the concept here is literally, look, at every one of these points. Look here. This matches up with this. This matches up with this. They all match up throughout the process. This is a time lapse or like a slow motion version of this object. This one being dropped, this one being launched horizontally. Now, obviously, this one travels some displacement in the x direction. Right? There's some horizontal displacement for the yellow one. What's the horizontal displacement for the red one? 0. The horizontal displacement, remember, is how far it moves this way. The red one was just dropped, so it did not move left to right. So the red ball on the screen, its horizontal displacement is 0. The green one, it has some value. Now, what's important is this. The time is the same for both, for this to fall. Okay, again, because the vertical initial velocity, we'll call that VIY, is 0 for this one. Well, over here, the vertical initial velocity is also 0. It's the horizontal velocity that is some number. Okay? Again, the vertical velocity for the red object is 0. Well, the green object, its vertical velocity is also 0 to start, because it's only moving horizontally. It gets launched horizontally. So that's some number. But this has no horizontal velocity. This is a true free fall. 0 vertical, 0 horizontal. That's this right here being depicted in red. But the green one is shot out horizontally. So we have to consider the fact that it has some value of initial velocity in the x direction. Whereas the y direction, its velocity is 0. Okay? So we're going to see the beginning of this section, and we're going to see that the angles are not as much as necessary. It's the second half of this section where we're going to utilize those angles. Okay, so let's take a look at this. So example 1, a bridge is 300 meters above a river. Tom Cruise jumps off the bridge to avoid some sticky situation he's gotten himself into. He jumps off the bridge by running off the edge of the bridge in a horizontal direction. So imagine that your desk is the bridge, and he literally just runs right off the edge. Like he's running from somebody behind him and he runs right off without noticing. It's the same thing as the tennis ball falling.
It's like a bird, like stays there for a second.
Yeah, you see those cartoons where like the road runner runs off a platform and he like stops and he's like, and he tries to get back and then you see him fall. Why the coyote or
this road runner gets across the top.
You're right, coyote chases the road runner. That's the whole idea. So yeah, with a wily coyote, he realizes he goes off the edge of the cliff and he looks back and he tries to reach for the cliff, but he just starts to fall. Obviously, he would never pause, right? But in reality, he would run right off the cliff and it would be the tennis ball rolling off the table. So it's just like a free fall. This is a free fall, but with some push in the x direction. But in the y direction, it's a free fall. Okay? So we're going to approach this problem and figure out that if the horizontal displacement from the bridge. He lands 50 meters from the bridge in the water. What is the velocity? What is the velocity with which he jumped? Okay, so if I drew a diagram of this, I'd have this person running this way off of a cliff. He then follows this path, right? Some sort of half parabola, because it's not, remember, we're not launching an object this time. The object is rolling off the table. When it rolls off the table, it falls with some parabolic motion, but it's more of a half parabola than a full parabola. Okay? So that's literally what this is doing. The tennis ball is rolling off the table and it will roll like that. That's what Tom Cruise is doing. To answer these problems, what you need to do is separate the vertical and horizontal components. So let's make a little like T-chart. Let's split up our page. We know that the bridge is 300 meters, by the way, above the river. And he lands out here, which is not drawn to scale, 50 meters out. Okay, this is not drawn to scale, obviously. Okay, because 300 is clearly more than 50 there. Okay, not drawn to scale. Now, we've got two directions to take a look at. Our x and our y direction. You could write horizontal and vertical if you'd like, or just write x and y. Either way works. Okay, but we have two things to worry about. In the x direction, what do you know? What do you know about horizontal parts of this problem? Give me something horizontally about this problem. I can't hear you. He moves horizontally after leaving the bridge 50 meters. So what variable would that represent? Good. The horizontal displacement x is 50 meters. And he moves to the right, so it's positive 50 meters. In our diagram, at least, right? What else? What do you know about the vertical direction then? The vertical direction, LT.
So negative 300.
Very good. And notice LT recognized the negative because he's moving down. Okay, it's got to be negative. If you get that negative, this problem will not work. Okay, it literally will not work. What else do you know now? Those are the easy parts for sure, right? Because it's on the diagram, which helps. What else? What are the keys, Carol?
You know the total displacement?
You really don't, because it's a curved path. You can't use the hypotenuse here. But I like the idea. You could figure out the hypotenuse, but that is not the distance traveled, because this person follows some curved path, so it's not a direct line. But I like the idea.
The vertical acceleration.
The vertical acceleration is always gravity. Good. The acceleration in the vertical direction, I'm going to call that AY. I'm going to put a little subscript with a little y there. And that's negative 9.81 meters per second squared. Siobhan, was that what you were going to say? Okay, there's more though. Can anybody else tell me more about this? Yeah. Not for the horizontal, but the vertical. Let's go over this. So remember, the tennis ball is moving which way right now? Good. This is Tom Cruise running back and forth. Not sure what he wants to do. Going crazy as he always does. So he's trying to figure it out, and then all of a sudden he decides, oh no, I'm just going to run right off the bridge. So when he runs off the bridge, he was still moving horizontally to start, right? So he's got some horizontal velocity. We don't know what that is. But we do know in the vertical direction, he was not moving. So the vertical... But put VIY there, please. Okay, in the vertical direction, Tom Cruise is not moving. Remember, he was literally moving left to right. When he jumps off that bridge, imagine he just runs right off horizontally. He's not jumping at an angle. He's not diving down into the water. He just runs right off. Okay? Yeah, who would ever do that, right? Run right off.
Would you be able to find the acceleration of the object? Would you be able to find the acceleration of x technically? Because you do like.
Remember, we're saying that in the x direction there's no acceleration because there's no air resistance.
Oh.
If we included air resistance, we'd have a sub x. But a sub x is always going to be 0. Okay, the acceleration of the x is always going to be 0. The reason is this, ready? Here's Tom Cruise running with a constant velocity right off the bridge. Okay, he's not running with some accelerated velocity, and it wouldn't even matter. If he started running slow and accelerated while running still, it's the instant that he falls off the bridge, that's his initial velocity. Whatever the velocity, let's say, ready? I'm running on one side of the bridge, 2 meters per second, 3 meters per second, 4 meters per second, 5. And when I hit 5 meters per second, I run off the bridge. That's my VIX, 5 meters per second. I don't have to worry about acceleration. I don't care if he accelerated prior to that. What matters is from when he gets launched off the bridge. When he gets launched off the bridge, he's got some initial velocity. That's what we're trying to figure out in this problem.
But wouldn't he have acceleration if he's like running fast?
Prior to it. Prior to falling off the bridge, sure. But imagine, right, if you're running with a constant velocity, what's your acceleration? It's 0. Remember, constant velocity means you're not accelerating. So I could be running across the bridge with a constant velocity and run right off. My acceleration would be 0. Even if I'm speeding up, as I'm running across the bridge and getting faster, it's the instant we leave the bridge. That's the velocity we're concerned with. So that velocity, that instant beforehand, is what we're trying to figure out. Okay, that's what we're trying to figure out in this problem. What don't we know that is involved in this problem in both x and y direction? There's another variable that we haven't talked about yet. Aiden?
Well, I was going to say we don't know how much he ran before the jump.
Correct, but that's only the x direction still. There's another variable that involves the x and the y direction. And it would be useful for us to know that, Christina. That is also involved, you're right. But that's not going to help us. But final velocity, you could find in x and y direction. This is going to be tough to find those. Time. The time it takes for this object to fall is the same in both directions. If I throw this object off here, right, the time it takes from when it leaves to when it hits the ground. If I find the time in the x and I find the time in the y, it's the same thing. It's time is time. You can't break up time into components. So let's write this down. Time is unknown, but since it's on both sides, we can call this our linking variable. I call it the linking variable for a reason. And you're going to see another thing this year that's called the linking variable also. The reason it's called the linking variable is because it links the directions together. It's the one thing that is constant in both x and y directions.
Is this always true for everything?
Yeah, for any two-dimensional problem, time is always your linking variable. So what we need to do, really, and this is where it's going to get a little bit tricky, but you got to go back to chapter 2 and think about those formulas we learned. We're going to relate the x and y directions to each other, but we're going to solve them independently first. So, remember a moment ago when I had Chris and Francis roll the tennis balls? We said that the time for a free fall, right, is the same as the time when it's moving horizontally initially. So what we can do is we can find the time over here as if it's a free fall in the y direction. We'll do what?
Make it equal to that.
And then we can find VIX. So let's go to the y direction first. There have been so many sirens today, it's unreal. Can somebody do me a favor, close that window? Let's turn the air on for a little bit, maybe. I guess, seriously, they're after me. 77, yeah, it's the Lex, Lenox Hill. But today I've been teaching in this room, like this is like the 10th time the sirens went off. Okay, so in the y direction, what am I missing that I don't know at all in this problem? There's something I don't have at all in this problem. Christina mentioned a little while ago. What was it? Yeah, you have no information about final velocity, which means that you're probably not going to use Vf equals Vi plus At. You're not going to use Vf squared equals Vi squared plus 2Ax or 2Ay, depending on the direction. So you're probably going to use that third formula. That third formula says, either, depending on the direction you're in, x or y, it depends, y equals Vi t plus 1/2 a t squared. Notice I'm starting to put subscripts everywhere now. Why am I doing that?
You can tell it.
To distinguish between vertical and horizontal velocity and vertical and horizontal acceleration. So these little y's you see are not variables, they are subscripts. They're identifiers. Okay, again, this is not a variable, this is not a variable. This is a variable y. This is a subscript, meaning velocity initially in the y direction, acceleration in the y direction. Why don't I need a subscript for time? Sam? It's the same for both of them. Good. It's the same unknown value for both directions. So if I call it ty and then tx, they're the same thing now. So in this problem, I could go ahead in the y direction and drop this off right away. Why can I do that? Because what is 0? Yeah, initial vertical velocity. Remember, this, take a look again, is the same thing as a free fall in the vertical direction. So you could literally approach this problem like it were a free fall, even though little Tom Cruise is running off that bridge. So we could find the time it takes, go ahead and solve for that, find the time it takes for this object to hit the water in the vertical direction.
When does the quadratic equation start coming in?
When we have VIs, which is going to probably be in a little while. It'll be in this section for sure, but we may or may not get to it today. I want to do a lab in the second period. I don't want to do a double lecture, so probably not going to get to it today. If I were to solve for t in a formula, I'd get rid of 1/2 by multiplying by 2.
Yeah.
I would get rid of a by dividing by a. Thank you for ever agreeing. I think, was that you, Ariane? So I divide by a next, and that's ay I should really put, right? Ay every time. And then take the square root, please, at the end. If you take the square root of both sides, the square root of t squared is just t. So the square root of 2y over a is our answer for the time it takes this object to hit the ground. You did this in test 1, whether you realize it or not, except we just didn't have subscripts at that point. So that's what it looked like. Test 1 was a problem where an object was dropped from rest. You had to find the time it takes and all this. This is the formula you could have used. It actually was nailed, right? Remember? You headed the ball up in soccer, and we said how long does it take for that object to return back to the ground? And you could have simply used this equation right here. These equations are not going to go away. So if you struggled on the first test, it doesn't mean just ignore this. It means that we have to correct any errors that happen. Plugging in. Okay, that's what I'm going to have right there. Plug in your values, please. See, if you forgot that this was negative, what would have happened? Yeah, the time would have been imaginary, actually, because it would have been under the rabbit. Imaginary. Have you learned about imaginary numbers yet?
Yes.
You would have had a negative under the radical, thus imaginary. It is not, though, clearly the case, so we get an answer, which is? Nick?
7.82 seconds.
Thank you, Nick. 7.82 seconds is the time it takes. Now, again, back to this example with the tennis balls. If it takes this tennis ball 7.82 seconds to fall, it takes the same tennis ball moving horizontally 7.8 seconds to fall, assuming they fall from the same height. So I can literally go like this, right? And they hit at the same time, even though this one was moving horizontally first. So this time that it takes is the same time we're going to use now in the x direction. So let's go back to the x direction. Go back to the x direction now. I have to slide this down so you can see it. So the 7.82 we could put in right here now. That was in the y direction we did all that work. That's why I was doing it on this side of the page.
But it obviously takes longer. I mean, as a ball, it's the same time, but this.
It takes the same time though. It literally takes the exact.
Because even if you like drop it first and then like at the
if I had a precise mechanism to do it, it would literally hit the ground at the exact same time. Because think, what causes an object to fall to the ground? Which acts in what direction?
Yeah.
Which way? Vertical. The horizontal motion in the beginning has no effect on the vertical velocity. So it's the same exact thing. Like if I drop these two, they should hit at the same time. Maybe they didn't because of other things, but they should just drop. If I even move it horizontally though, it's not affecting the vertical velocity because it's moving horizontally. If I do this though, Sophia, that is different than this, right? Because that's going to be in the air for a lot longer. But if I were to literally, if I could somehow do this, where I was able to go like that, and they actually moved at the exact same time and left at the exact same height, that ball should hit the ground at the exact same time.
But if it can't with vertical time.
But if it comes off with any vertical motion, if you throw it down, if you throw it at an angle, if you throw it only horizontally, this works. If you throw this at any angle, which would give it some vertical velocity, this will not be true. It's only when something is fired horizontally that this is true. Okay? That's the only time that this is going to work this way specifically. Where did I put my pen? There it is. So, we use that time in the x direction. Now, in the x direction, I told you a little while ago that we're going to assume acceleration is what? In the x direction, right? So, when there's no acceleration, there's only one formula that you're going to ever use. The first formula we learned all year. Sam? Okay, there it is. This is the formula you will use all year for the x direction. V equals x over t. Why can I use that? Because there's no acceleration. Okay, there's no acceleration. Now, if there's no acceleration, what else do you know about the velocity if there's no acceleration? It is what? What's the term? A constant. The x velocity is always going to be the same throughout the process of some fall or some projectile horizontal motion. So if I do this, and I roll it, right? And I roll it with a velocity of 2 meters per second. Even while it's falling, its horizontal velocity is still 2 meters per second, 2 meters per second, 2 meters per second, because there's no horizontal acceleration. Remember, when horizontal acceleration is 0, the velocity is a constant. So we could even call this v bar if we wanted to, meaning constant. Focus, please. We could call it v bar if we had wanted to. So for this problem, if we want to figure out what that velocity was that Tom Cruise left the bridge with, just take 50 meters over the time you got, 7.82 seconds. That will give us the velocity, and you could put v bar x or vx or vix. They're all the same thing, really. I'm putting a little bar over it because it's ended up being constant. This velocity is the velocity that Tom Cruise ran with off the bridge. That will not change in the x direction. Remember, when an object is falling, the vertical velocity changes. The horizontal never changes. Write that down. The horizontal velocity will never change because acceleration in the horizontal is 0. So even while he's running off the bridge, his horizontal velocity is still whatever this answer comes out to be. Even as he's hitting the water, that's still his horizontal velocity. What does that come out to be? Siobhan?
6.4 meters.
Very good. Meters per second because it's velocity. That means, ready? Here's Tom Cruise, aka his tennis ball. He is running with 6.4 meters per second. He runs right off the bridge. He starts to do this. Well, he's picking up velocity in the vertical direction. He's getting faster. But in the horizontal, this is still his velocity the whole way through. Okay, in the second period, we're going to do a lab now. Now, before I give you a 3-minute quick break, over the next 4 or 5 days, I put up homework. The homework is to get started on the problem set. So next week, we're going to finish 3-3 on Monday. Or Tuesday, I forget which day I see you guys. But we're finishing it next week. Then we're going to have our test, I think, is at the end of next week. It's really pretty much 3-1, 3-2, and 3-3. That's it. So in the next 4 days, you need to do the problem set for 3-1, 3-2 to get those out of the way. Then try to start your homework for 3-3. You could do the beginning problems from the homework where it's fired horizontally. When it's fired at an angle, those are the ones that we haven't gotten to yet. Is that clear? Yeah. So you're not going to start those problems yet. When we get to the angular stuff, which we're going to do in the next class, we'll talk more about that. Okay, there is a second example. A C-130J Super Hercules plane flying 500 meters above the ground needs to drop an air package to soldiers on a remote island. This is physically how it's done. Okay, if the velocity of the plane is around 186 meters per second or 670 kilometers an hour, when it drops the package, how long will it take to reach the ground level? How far will the package travel horizontally before it lands? So we've got this, right? We've got a plane up in the sky. Wonderful image. Okay, it's traveling horizontally. That's pretty good, right? It's traveling. Say yes. We're kidding. It's traveling with a. Oh, it kind of is a dolphin or a fish. I always get fish and planes confused. They look similar, you know? So the velocity the plane is traveling with, right? Now, the person in there does what? He or she just goes, you know what? I'm going to drop it. I'm going to drop the package. So here, watch me. Ready? I'm the plane. Okay, I'm the plane. I'm the plane. I'm the plane. I drop it. Isn't that the same thing as rolling off the table? Because which way am I moving right now?
Horizontal.
And then I drop it. So it has some horizontal initial, but it doesn't have any vertical, right? I'm not throwing it down. I'm not throwing it at an angle with some vertical velocity. I'm not tossing it up like that, waiting for it to come back down. I'm moving horizontally and dropping. And it follows that parabolic path, the same thing as that. So this problem is identical to the last problem. Okay, we're just going to change some things up, find some different variables.
Right, but like, so let's say that the plane was, you know, it was slowly going down, or the cliff that he fell off had a slope.
Again, then it's not one of these problems. And then
Right,
we have to,
but I'm saying
we're going to
that's
approach that differently.
So the only way that these problems work is if the
Horizontal.
going has to be fully horizontal.
Yeah, absolutely. Okay, so with that said, the package that's being dropped, because of like basic laws of physics, is moving at 186 meters per second also. If the plane is moving that fast, so is the package. So when the person drops the package, it's got some horizontal velocity of 186 meters per second. So when we're looking at our diagrams now, in our xy, we can automatically say that Vix is going to equal 186 meters per second. Last problem, we determined Vix, but now we're given that value. How far above the ground is it? That? So y equals negative 500 because it's above ground and it's going to travel which way? Down. Our goal is to find what? How long it will take to reach the ground. That's time. And how far it will travel horizontally before it lands on the island. So we're going to eventually have to figure out time. And we're going to have to figure out x. Both of those. What else do we know about this problem? If it's only moving horizontally to start, what is VIY? Yeah. Again, remember, this object is the same as what Dano and Franken were demoing with the horizontal motion. It's only moving horizontally, so the vertical component of velocity must be 0 to start. In the x direction, we know acceleration is always 0. And what is it always in the y direction? Anybody? There it is. Okay, a number that I told you, I wasn't joking, you don't have to memorize it, but you probably will. You probably will memorize it. So look at the y direction. Isn't it the exact same problem as the last problem? So what should you do? Should you go through that whole solution again?
No.
Heck no, you shouldn't. T equals radical 2y over a. That's the answer. It's the same exact problem. Do you see how the beauty in physics problems exists? Different scenario completely. Now we're trying to find out horizontal displacement, but the y direction is analogous to the last example. So please don't redo the y direction. You could write y equals VIT plus 1/2 AT squared. Cross off VIT again and solve, but you will get this. Noting that that's a little subscript for y. Okay, again, if you need to see where this came from, this is the exact same solution from the last problem in the y direction. We drop off VIYT and we solve for time. What do we get when we solve this one for time? By the way, any free fall will use this, right? Look, I do this right now. What's the height? Maybe 2 meters? put a 2 in for y, or negative 2 in for y here, for minus 2 meters, you could figure out the time it takes to land. Okay? You could literally find the time it takes to land for me just to drop this by just plugging in whatever the height is for y. This always works for free falls. What do you get when you plug in negative 500, the height from the plane when it drops it? What do you get? 10.1. Others? It's going to be more than 7, because last problem was 7 something, and it was only 300 meters, right? When it was falling? This is falling 500 meters now, so it's got to be longer than 7. Yeah? 10.1?
Yeah. Oh, no, I didn't do it.
I'm just asking somebody else to confirm. Oh, thank you. Okay. So now that it's been confirmed, let's go over to the x direction. Well, earlier, we didn't know what the time was in the x direction, but the time is the linking variable. So what should you write down for time? 10.1, the same thing you got in the y direction. So although you may not be able to solve for time in the x, if you can solve for it in the y, just carry it over to the x, and it becomes your linking variable. Now, we want to find the displacement. We can only ever use this formula. It's the only formula we're going to ever use in the x direction because acceleration is 0. So multiply by time to get x by itself. (186) times 10.1. What do you get? 18? 18.
186 times 10.1 is 1,878.6.
Oh, my rest.
What does that mean?
It's a
Right. It's right.
It's a bad habit.
I've just been hearing a lot of it lately. That's why I didn't know what it meant.
I wrote it down.
It's like a chicken round.
My rest. Yeah.
Never heard that stuff. Is it even a word?
Yeah.
To roust up the crowd, doesn't it mean like to get them like rowdy?
It's an actual word, but the way I'm saying it is
It's like a chicken round. It's a big screw up. It's like
So, what we determine is this. I want to make sure we understand the significance of our answer. This is the important part of physics. Forget the math for a second. The important part is the significance of this answer. Here's the fighter jet, or the Hercules jet that's going to drop a package, right? Why do we care about the x value? Why is this important in this problem? Think about it logically. Theo?
because if they were going to drop a package, they want to know where it's going to land.
Yeah. If I'm flying that plane, I need to know if my engineer in the back tells me, all right, in 3, 2, 1, drop. Well, why did he tell me to drop in 3, 2, 1? Because he was estimating the time until it was exactly 1,878 meters from the island, and obviously there's room for error because the island is relatively big, but not much error. There's not too much room for error here. So when the island's here and the package is here, it knows to drop so that it will land on the island. Okay, so you're literally determining, the location from the island that you should drop it so that it does this. It lands smack on the island. Theo?
Wouldn't it have a different acceleration?
It would. And remember that we are physics students in 11th grade. And engineers in the military know how to incorporate air resistance. Absolutely. Absolutely. Okay, there would be AX in a real life problem. You would have some acceleration in the x direction. It wouldn't be this simple. Does that make sense? We've modeled it to be simpler because the knowledge is involved in calculus that something you haven't learned yet, so we just can't.
How would you then put those two together to figure out where to drop it? Like the AX and the AX.
Well, the AX you would have to consider in the problem. You could no longer use an equation like this to determine it. You'd have to use x equals VIT equals 1 FAT squared and solve the time, but it would be a quadratic. It's not hard. You could do it, but the issue is that to get AX, you need calculus, just to get the number, or whatever it is. Depends on the size, the coefficient of friction, the velocity of the wind. There's so much that goes into play. And you can't calculate AX without knowing. Okay? Listen carefully. I want to talk about a few things now. There's a lot that you need to do in the next 5 days. So either take out your planner or remember this. There's a lot of stuff for you to do.
Is it on the Moodle?
First, these two things are on Moodle I'm about to tell you right here. On Moodle I already wrote, next week we get back, we finish 3-3, we do our lab, at the end of the week is your test, it's on 3-1, 3-2, 3-3. So, over the week, you should do problem set from 3-1 and 3-2, which you can do at this point. If you're struggling with 3-1, 3-2, maybe you have to wait, but try at least. You could start the homework for 3-3. It's not due when we get back, but about half the problems involve only horizontally launched objects. If you see a problem in homework 3-3 that says it's launched at an angle, you shouldn't do it yet. Does that make sense?
Yeah.
Okay, those two things you need to do in the next 4 or 5 days. What else do you have to keep considering that we can't forget about?
November 5th.
Yeah, your projects. Keep your projects in mind. Okay, all the supplies are ready for me to build this ramp once I just have time to put it together. I've had no time. But I've got all the supplies, I cut all the wood, so I'm going to make that ramp at some point next week. I need to get the hinges. I'm waiting for Amazon to deliver them. Okay? I forget, to be honest, Katie. Take a look. I think it's at the end of next week, I think. Okay? So now we're looking at projectiles, fire, and angle. So let's remember the 2 rules that we looked at already. And we talked about this in section 3.1 and 3.2. That's why we did 3.1 and 3.2, honestly, for this piece right here. For the idea of an object moving with some sort of angular trajectory. So it's moving at an angle to start, or maybe it's finishing and it's landing at an angle. Either way, we need to know our components to do that. So we start with the fact that we remember that x refers to cosine and y we use sine. Now, what does that mean again? To recall, we're going to see in the next example here. So let's take a look at this next Tom Cruise example. We've got in another action movie. He has to leap from the top of one building to the top of another building. The second building is 4 meters away. It's pretty far. Ready? Just to give you an idea, right here. So 1, 2, 3, 4 meters. So from the podium to about right here, that's how far of a gap he has to jump across. Which seems impossible at first, right? But you also recognize that the other building is 2.5 meters below it. So he's not running and jumping and has to make it to land there. He's got to make it to land 2.5 meters lower. So he's got a little bit of room for, not error, but a little bit of space. So if we're drawing this, here's what we have. Okay, that's the situation. Tom Cruise is running and jumping. We're going to see that he gets a running start this time, and he realizes he screwed up when he ran off the bridge that time, remember? Remember he ran off horizontally? He's like, oh, it's kind of stupid. He should probably just stay at home, I agree. But, you know, he's stuck in his movie again. So he realized running off the bridge didn't work too well, so let me jump at an angle. So in this problem now, this is where we get to our angular stuff now. He jumps off the bridge, off the building at an angle of 15 degrees. Okay, there's our 15-degree angle right there. So that's Tom Cruise. He's running, he's running, he's running. He jumps 15 degrees off the flat roof. Now, we know that the X gap in the middle there is how many meters? This gap in the middle? 4 meters. And what is the vertical displacement that he will undergo if he just makes the jump correctly? How far is that? 2.5 meters. Okay, that's the gap between here and here. Okay, from building height to building height. So that's the kind of problem we have as a setup. So for all of these problems, I highly, highly recommend that even if you draw a quick sketch, something in the beginning to give you an idea of what you're dealing with. Okay? So that's the info we know so far. We know that he ran, let's see, with a velocity of 5 meters per second. That was his actual velocity. Okay, after getting a running start, he jumps at an angle of 15 degrees with respect to the flat roof while traveling at a velocity of 5 meters per second. So the velocity is 5 meters per second. Now, in the last example the other day, that velocity is supposed to be meters per second, okay? That's M over S. In the last example the other day, since he ran only horizontally and he didn't jump at an angle, his initial velocity was all horizontal, right? That was the horizontally fired projectile. That was the whole lesson. Now it's not horizontal, it's at an angle. So he's kind of running, right, horizontally, but he's also kind of jumping vertically. So this velocity vector, V, has what? Yeah, both x and y components to it. So in this problem, we're going to have a VIX and a VIY. Both. It's shared, and it's based on the sine and cosine. Yes, and it's shared. Very good. Good work. It's not like it's split evenly, though, right? It's not like one's going to be 3 and one's going to be 2. It doesn't work that way. It's a factor of the angle that you jump at. So let's explain what we're going to do to figure out what those V values are. So this is literally everything in the problem right here. The question, by the way, is will he make it to the roof, right? Will he make it to the other rooftop? That's the question. I'll leave the question at the very top. All right, now, the thing in physics is we assume that objects moving in space are a point, a finite point in space. So although Tom Cruise has his arms and legs that he can kind of grapple onto the wall with, we're assuming that he's literally a point in space that is running with no legs because it's a point in space, and then that point in space goes off for 15 degrees, and will that point in space land on the other rooftop, or will it fall to his death? Okay? But you have to assume that Tom Cruise really doesn't have arms. You can't account for his arms and reaching and stuff, right? So if he hits the wall right here, right, he doesn't make it. Okay, so if he hits, let me use the pointer so you can see later. So if he jumps off this wall or off this roof and does this, he's good. That's Tom Cruise, the little red dot. But if not, if he does this and he hits even right here, we can't assume that his arms are long enough to reach and pull himself up. So if he doesn't make it to here, okay, or higher, I guess you could say, either land like here and then he'll follow on, or maybe up here and follow over, or here and continue. But the minute he does this and ends up down here, he's not on the second roof. Or doesn't make it. Yes, let's assume his feet have to make it to the roof. That's an easy way to think. So, with that statement made, we need to take a look at our different components, x and y. So in the x direction, what's going on in the x direction? Give me one piece of information.
You have to make 4 meters.
Yeah, we definitely know
Displacement is 4 meters.
displacement is 4 meters. Now, this is where it gets a little bit tricky. They're given both the x and the y displacements in this problem. Technically speaking, you could deal with either of them. But you can't deal with both of them. Because if he ends up 4 meters over and 2.5 meters down, the problem works out. But the question is not that that's going to happen. The question is, will he make it? So our question really now is to figure out how far he falls vertically. If we're going to let x equal 4 meters, we have to find an unknown value of y, if that is the case. So think about it for a second. If x is 4 meters, we do all this math, solve this equation, we get a y value of -2. Does he make it or not?
No. Yes, he does.
Think about it again before you answer. Okay, so let's go through this. If we do all this work in a moment, and we end up getting y equals -2, that means that he started here, and he ended up 2 meters below it, but over here. So would he technically make it if he did this? Yeah, he'd make it, because he'd be right here, and he'd continue to fall forward onto here. But if you get an answer of like y equals -4, that means that, where's -4? Well, here's -2.5. -4 would be like down here, right? From the starting, this is the starting. If this is 2.5 meters below, -4 would be like down here. That means that if we get -4 for y, he does this. And hits the wall right there. Does he make it then? He doesn't make it. So our goal is to figure out the y value, actually. Our goal is to figure out what is the y value. If the y value is something like -1 or -2 or -0.5, then yes, he only jumps and falls a little bit and he makes it. But if you get a y value of -5, then he clearly doesn't make it. Now the other way to approach this problem is to set y equal to -2.5 and see if he makes it 4 meters in distance.
They kind of give you too much information. You kind of can pick which one you want.
Yes, you can pick either one. So if I let y equal -2.5, then I'm saying the following. I'm saying after he falls 2.5 meters, is his x going to be 4 or not? Then you'd have to test out what x is. If you get an x that's greater than 4, or equal to 4, it means he made it. If after 2.5 meters down, his x displacement is only 3 meters, he's right here then. Here's 3 meters, here's 2 meters, here's 1 meter, here's 0 meters, right? 0, 1, 2, 3, 4 meters. So if you set y equal to -2.5, what you could do, and you get x equals to like 3, it means that he would fall 2.5 meters and be only 3 meters across, which means he would not make it. He would fall to his death. So either one of these could be unknown, but you have to know one of the two. So you pick one of the two, really, in this problem. I'm choosing to say that x equals 4 and hope that we can get a y value that's not more than 2.5 meters, so he makes the actual jump. So let's take a look and see what we can do for that. So if that's true, we also need to write down our other given information. What is VIX and VIY in this problem? And if you're forgetting how to do this, go to the previous slide, scroll up to the last slide, look at the formula for VIX, look at the formula for VIY, and tell me, I don't want to know the number, but tell me what I'm going to multiply, what am I going to actually do to get VIX and to get VIY? What am I going to do to get VIX and to get VIY? Aiden?
VIX would be 5 times cosine of 15.
Very good, Aiden.
And then VIY would be 5 times the sine of 15.
Very good. Okay, again, in the previous class, we did the beginning of section 3.3, which involved only horizontally fired projectiles. So everything was in the x direction. We put whatever the velocity was in the x. We didn't even worry about cosine because there was no angle. And we let VIY equal 0 in that problem. But now, we're looking at where it's launched at some sort of an angle. So there's a component in the x and the y. Now, those are numbers, obviously, right? 5 cos 15 is a number. 5 sine 15 is a number. So we can utilize those numbers. For 5 sine 15, I get 1.294. For 5 cosine 15, what do we get? Somebody tell me that one I haven't written down. No?
4.829.
Why is the velocity in the x direction so much bigger than the y direction here? Who knows their, I don't want to say common sense, but who can use logic and deduce that answer? Why is the x velocity much bigger than the y velocity for this problem? Yeah?
Because that's like, for x, that's like the distance away from each other. Because it's the horizontal plane.
It's not that. I get what you're saying because the 4 versus the 2.5. It's not that. It's not the measurements of the displacements. Good idea, but it's not. It's just coincidence that the geometry works out that way.
Is it because he's running and so he would have more velocity running than jumping?
Logic, that's a good logical answer. He's running this way, right? And he's going to jump. So most of him is going that way. So most of him is in the x. But how about mathematically, from what can you see?
Well, I mean, basically it says that he has 4 meters to go and it's going down.
It's not the geometry again, though. Remember, I just said that, guys. Listen to each other. 3 answers. You all give the same answer, 3 of you. Okay, I get the idea that you're getting at because 4 and 2.5. It has nothing to do with that. It's something that's indicating that gives you more x than y. We did the lab simulation here already, right? Remember that kicking the football and throwing the football, that little simulation? Think back to that simulation. How do you get more in the x than in the y?
Does it have to do with the angle and it's an acute angle?
Yes, the angle is not just acute, but less than 45.
Yeah, that's right.
If you recall from that lab, 45 degrees was a key angle in that lab, or around 45. Usually gave you that maximum range in the lab. If you're not getting that from the lab, you can take that note down, you're welcome to. Okay, but 45 was the angle that gave us max range. Well, anything bigger than 45 degrees, you'll have more y velocity. Anything less than 45 degrees, you'll have more x velocity. Okay, so this angle, he's literally doing this. He's running and jumping at like a 15-degree angle. He's not jumping up. He's not jumping like this. It's not a punter that punts the ball straight up. It's like a kickoff kicker in the beginning of a football game. A field goal kicker actually has to get some elevation to get over the defensive line. But a the kicker that kicks the ball off after a touchdown or any score, right? Kicks the ball mainly horizontally. He does not kick a lot into the vertical there. The guy who's kicking the ball off at the very beginning of the football game needs to kick it from the 30-yard line all the way down to the end zone. He kicks that at a low angle, so it gets a lot of x velocity. Whereas the punter punts it at a very high angle, and it gets a lot of y velocity. So as this angle increases, As this angle increases, there's more velocity in the y. So if we use, instead of 15, if we use the bigger angle, like 35 degrees, there'd be more in the y, a little bit more in the y, and a little bit less in the x, until we got to 45 degrees. If you put 45 degrees, it turns out that the cosine of 45 and the sine of 45 are the same number. Okay, because 45 splits 90 in half, right? So if we use 45 here and 45 here, these would be identical. Because 45 is literally halfway between 0, which is all x, and 90, which is all y. So if you're at like 85-degree angle, it's mainly going to be y, and this would be a much larger number, and this would be a much smaller number. Okay, so these are good things to pick up on, trends, and you're going to see that. And a lot of that comes from knowing your angles as well. Okay, but that's tough, because in your pre-calc or in your Algebra 2 class, you haven't done that yet. Okay, so I'm trying to give you a little preview of what you can expect. Back to the question at hand now. We also know some other information. We know that in the y direction, acceleration is always what?
Negative 9.81.
Okay, if you didn't write that down like 37 times now, write it down for the 38th time, please. Okay? Acceleration is always negative 9.81 in the y direction. I'm not going to try and like trick you and be like, all right. So, if I said to you physically, we are now on Jupiter, where the acceleration of gravity is negative 22.9, which it is, you could just use that number. But it's not, I'm personally not going to do that, to tell you that, okay? In the x direction, what's the acceleration always? Always going to be 0. Remember, gravity is only pulling you down. Gravity doesn't pull you left or right. The only thing that would affect you left or right is like a rocket booster on your back. Imagine like a rocketeer. You guys have like a rocket booster and he's flying. Yeah, then it could force you forward, and then you'd have x acceleration. But this person, Tom Cruise, is just jumping off the bridge. His initial jump is propelling him forward, but there's no acceleration that's pushing him forward even more. It's just his velocity. We're assuming that the wind is not slowing him down. Had it been, you'd have some negative acceleration in the x direction for the wind slowing you down. Tom?
Wait, so for acceleration on the x, it's always 0 on every problem?
Any projectile motion problem we're going to do, it's 0. If you go like on a midterm exam, you're going to have a problem maybe where an ice skater is sliding or a person is moving or something horizontally. You're going to have acceleration, like a car can accelerate.
But the other goes down.
But I'm talking about free fall motion, where an object is launched and then it's just moving. When it's moving through the air, you can't have horizontal acceleration because we're assuming no air resistance. Okay? Because of that assumption. With air resistance, a lot more has to be taken into account. Okay, so the problem really, again, is to figure out the value of y. What is the linking variable that's on both sides of this? The linking variable. Time. Time is the thing that you can get in both directions to help you. And if you get the time in the x, it's the same as the time in the y. So look at your y direction. This is where I think a lot of you struggle on tests because of the fact that a test is timed, right? And you have to sit there and figure all this out much quicker. So here's my approach if I were taking this as a student. I look at the y direction, I say to myself, how many unknowns do I have in the y direction?
1, 2.
2.
Oh, 2, sorry.
T and y, they're both unknown, aren't they? Yeah. So there's a good chance I probably can't start here, so where should I go?
X.
With the x direction. How many unknowns?
1.
Only 1. And we're only ever using one formula in the x direction. There's one formula that we will always use in the x direction. Does anybody remember what formula that is? It's the first one of the year. Yeah, there it is. V bar equals x over t, or Vx equals x over t, or whatever you want to call this subscript here. Why do I call it V bar? Because although it's initial, it is constant. Very good. Although the Vix is 4.829, since there's no acceleration, this velocity is never going to change. Remember, velocity only changes due to acceleration. So right now, the Vx we're going to get is 4.829. I can go right there. I can put a 4 in for x, and what can I solve for in this equation?
T.
Solve for time. Either rearrange it, flip-flop, right, remember this? Just flip them. Okay, just switch these two positions right here, and then plug in the x and the Vx. What do we get? You got an answer?
I got 1.2 meters.
It's not 1.2. Be careful. And we're looking at time, right? So it's seconds. 0.82. I think you did the inverse. I think you flipped it. 8.3, I guess, right? Technically? What do you got? 8.3, really?
Yeah.
8.28. Yeah, so I'm going to do 8.3 for now. That's how much time it takes Tom Cruise to move 4 meters horizontally. Now the question is this. How far does he move vertically in those 0.83 seconds? In the 0.83 seconds it takes him to do this, ready? In the 0.83 seconds it takes him to do that, the question is how far does he move vertically? So let's solve for y in the y direction now using this time. Because this time is the same time it takes him. So it's both directions here. If I want to find the displacement in the y direction, what formula is the only one we have that doesn't involve VF? Because we have nothing about VF here. Notice there's nothing about VF. So we can't use the VF formulas. There's only one other one that doesn't have VF. Chris?
Y equals VIY T
Plus 1/2.
AT
squared. Good. And notice I'm putting little y subscripts everywhere like Chris was mentioning. Again, this is a subscript. VIY. IY is a subscript. The AY, the little y here, is a subscript. It's not a variable. It's not a variable. It just designates that this is the velocity initially in the y direction. The acceleration where? In the y direction. Simply because it differs in the x direction. So we want to figure out what y is. Let's just go ahead and plug in. So VIY is 1.294. Well, where did we get that? We did it right up here earlier. It's the velocity he jumps off the bridge with, or off the roof rather with. Times the time, 0.83. Plus, I'm running out of room, so I might slide over for a sec here. Plus 1/2 times A times T squared. You definitely are going to get a negative answer in this problem. Well, I shouldn't say definitely, because he could, based on the context, he's going down. But technically, he could have been rising up at some point throughout the process of this. But we're going to get a negative answer. What do we end up getting as our answer for this? Again, I encourage you to practice. If you're sitting there and watching, and you have trouble on the test, I'm going to have very little sympathy, if none, for you. Okay? Lil?
I got negative 2.29.
That's it, though. So how much room did he have? He had 2.5 meters, which means he just made it. Think about it. Let's go over the physics of the problem, or the geometry of the problem. Here is the building 1. Here is building 2. Tom Cruise jumped and landed 2.3 meters below after 4 meters, which means he's right there at that instant. Okay, this is a 4-meter jump right here. And he dropped 2.3 meters. And how much room did he have to drop? He had 2.5 meters to drop. So that means he's right there, which means if you continue this path, he will end up on the actual roof. Okay? After 4 meters in the x, he is 2.3 meters below where he started. He went up, came back down, ended up 2.3 meters below, which means that if he continues along this path, he will end up on the actual building. What kind of an answer, or give me an example of an answer that meant he would have fell to his death? And? 3. What else? Negative 3, obviously. Negative 3. What else? Negative 4. Anything bigger than negative 2.5 in absolute value, really, right? Anything more than the 2.5 meters he had to spare means he would have hit the building. If the answer were negative 3, he would have hit right here on the building, right? On the actual side of the building. If the answer were negative 4, he might have hit down here. Negative 5, he might have hit down here. But either way, if it was beyond the 2.5 meters he had right here, this is 2.5 meters, he'd have ended up down here, or all the way down here somewhere, or just somewhere literally down here. Tom?
So, for x, you say it equals 4 meters?
Correct.
I'm just confused. Why is y a question mark when y
So, if we let y equal 2.5, we would have to determine x to see if he made it to 4 meters or not. Because we know the geometry of the building. We don't know the geometry of his jump. They're different things, right? The setup gave you the geometry of the building, which told you it was 4 meters apart and 2.5 meters below. But that doesn't mean that's what his jump is going to be. The question is, what is his jump? Will his jump fall within the parameters to survive? So one of those had to be unknown. Either you let y equal negative 2.5 and find x, hoping that x is more than 4, so you made the 4 meters, okay? Or the other way around.
So, let's say on another problem, if you were given both, would you do the same thing?
You could be given both sometimes, but then another kind of a problem you might be asked like to find the velocity instead to do that. But you were given all the other information. So your question here was, is he going to make the jump? Well, is he going to make the jump is a function of his displacement. So that has to be unknown. Right? If you think about it, when you're told, will he make the jump, it means, will he cover enough distance or enough displacement in that problem? So one of the displacements has to be an unknown in that problem. Okay? The problem we're doing now is not like crazy difficult, but this is definitely not an easy problem we're working with. Okay? Let's look at another example to see. So when you're doing your homework, when you're working on this homework, I recommend maybe looking at the example in the book too. Or at least practicing through some of these. I hope you get through the last one. Probably not going to. Salmon often jump over waterfalls when swimming upstream to reach a breeding ground. Starting 2 meters from a waterfall that is a half a meter high, at what minimum velocity? So here we go, Tom. So now we know the salmon's 2 meters from the base of the waterfall, and the waterfall is a half meter high. And we're told, what is the velocity that the salmon has to jump with to make it over the waterfall? So now we know the values, 2 and 0.5. They're definitely going to be there, but now we're looking for v. So here's the salmon. Here's the water. The salmon is, here's the waterfall right here, some rocks and this little waterfall, right? So the salmon's making this jump at an angle of 32 degrees. The distance away is 2 meters. How do I know that the 2 meters is the x? Yeah, starting 2 meters from the waterfall. How are you from a waterfall? You're away from it horizontally. 2 meters from the waterfall. And it simply says a moment later that, look, the waterfall is 0.5 meters high. Not drawn to scale. This is not drawn to scale. Okay, so we know the geometry of this problem. It's given, and we know that the fish is going to make it. It says, what's the velocity needed for this salmon to leave the water and make it over the waterfall? So in this problem, we have our x and we have our y. Whereas the last problem, we were trying to figure out, will Tom Cruise make the jump? The question we're looking at, well, we know the angle is 32 degrees, sorry. That's 32-degree angle right in there. The question we're looking for is, what is the velocity with which this salmon needs to jump to make it? How will the salmon make it? So we have to start by listing what we know. Okay, let's look. I'm gonna scroll down because we have everything in the diagram now. What's the displacement the fish will undergo in the x direction? 2 meters. And if the fish just makes it, the vertical displacement would be? Good. And technically, it'd be like something greater than or equal to, really, right? Greater than or equal to 0.5? Because the fish could make it by another half a meter if you increase the velocity. But we're trying to find out the minimum velocity necessary to just make the jump. So let's say our answer comes out to be 8 meters per second. That means that 9 meters per second, the fish would clearly make it by a lot. 10 meters per second, the fish would make it by even more. But anything below, whatever the answer comes out to be, the fish is not going to make the 0.5 meter jump. Okay, so we could say it's...
Would the velocity be shared or would it be for y?
It would be shared, because it's at an angle. Take a look at the angle, right? So let's write our VIX. We don't know what the initial velocity is. That's what we're looking for. But we do know that we take that and multiply it by cosine of 32 to get the x component. And in the y direction, what do?
You multiply by the sine of 30.
Yeah. But what's unknown here?
Is this on the sheet for equations or whatever from this?
This right here?
Yeah.
No, this is stuff that we did in section 3.1 and 3.2. Remember your vectors for 3.1 and 3.2? That's where that's from. So the unknown in this problem is v. V appears here and v appears here. So it's on both sides So either we solve for it on one side, or solve for it on the other, or possibly we might need both sides to solve for it together. Because what else is unknown besides v? What's the linking variable? Time. So we have, time is usually missing in a lot of problems. So we have time that's missing and v that's missing, both. Okay, so here again we know that ax is 0, ay is negative 9.81. Time is unknown on both sides. So we're going to have two variables unknown, time and v, and it means we're going to need two equations, clearly. Let's look on the left-hand side. For the x direction, I could use this formula as always. Remember v bar x or vix or whichever vx you want to call it, but it's this value right here.
We don't have.
Okay, but we don't have v, right? And we also don't have time here. So this is probably not going to work. I'm going to plug it in just for the sake of it for now, and I'll explain why in a minute. I'm going to put v cos 32 equals 2 over t. I'm going to plug in what I know. I know that the x value in this problem was 2. So I'm going to take this 2 from the top here, plug it in for x. I'm going to take vix, plug it in here for v bar x, the same thing again. But again, we don't know time or velocity. So we cannot solve this side. So where do we go if we can't do anything there? Yeah, we go to the other side automatically. If we go to the y direction, again for this problem, we have no information about vf. So there's only one formula that we can use, and it's the same one as the last problem. That formula is y equals viy t plus 1/2 at squared. Yeah, you're going to need to use substitution method here. It's not going to be system with elimination, but substitution.
Where you solve that side.
Correct, and plug it into the other one. So let's plug in. What do we know about y? What's the height that the fish is going to jump? Yeah, 0.5 meters. I usually don't plug in, but you'll see why in a minute why I plugged in here. VIY is V sine 32. Times time plus one half a t squared. Well, take a look, folks. What's the problem? Look at both of these equations. They're both missing time and they're both missing velocity. So you can't solve them separately, which is where a system or simultaneous equations come in. So use substitution method. Our goal is to find velocity, right? That's our goal, to find velocity in this problem. So let's go ahead and isolate t in this equation. Isolate t, and wherever there's a t here, we can plug in for this t and for this t and later on. So how can I isolate t here? What do I do to get t by itself?
You can multiply. Yeah. You can multiply. Oh, you can switch out the.
Flip-flop.
Yeah.
Okay, don't even think about multiplication. Come on. 2 over v cos 32. Okay, so literally, flip the v cos 32 and the t, switch their positions, giving you this. This is the expression for time.
You can plug that back in there.
Yeah, take that whole expression for time, right here, which looks like an answer, but it's in terms of v, and plug it in right here, and right here. This is substitution method that you learned in your freshman math class. So we now have 0. I'm going to write out the y equation, the whole thing, once I've plugged in for that stuff.
Should you solve for sine of 32?
Yeah, you can get a number for that if you want. So it's going to look really complicated because you're going to see a lot of things with v in different places and sines and cosines. But the only thing you have to concern yourself with is really this v over here. Reason being, what happens to this V and this V?
Cancel.
Yeah, they cancel. That's your basic laws of any variables. You have a variable in the numerator and the denominator, you can cancel because this is multiplication, really.
But even though they're
Sure, because this is really, remember, this is really over 1. There's a time symbol there, there's a time symbol there. So the V here cancels that V right there. Those drop right off.
the cosine.
They don't drop off, no.
They say.
Correct. So let's continue solving this equation. I know, it seems intense. It's all right. Now, half of 9.81 is negative 4.905. I'm going to write that out. Okay, and then this is over 4v squared cos 32 squared. Why did I make it 4? And why did I make it v squared and cos 32 squared? Where did I come up with these three? Why did I do that in here? Yeah, remember when you square something that has multiplication and in division, you square every single term. And this with a plus sign, you can't do that. So 2 squared is 4, v squared is v squared, cos 32 squared is cos 32 squared.
Question, the 2 and the 2, that canceled out? And 1/2 canceled with that 2?
No, this 1/2 times negative 9.81 is negative 4.905.
Alright, gotcha.
I just simplified that. Now, this is all numbers at this point. The rest of it is numbers, so you have to figure out what your numbers turn out to be. So this whole value right here, I'm going to highlight it, is a number. Type in your calculator, sine 32, hit enter, or close your parentheses. Remember to close your parentheses after the 32. Multiply that by 2, divided by cosine 32. What do you get? Gabe?
1.24425.
25 if you round properly?
Yeah.
All right. I'm going to assume he's right unless somebody tells me differently. 1.25? Okay. Now, take a look over here. 4.905 can be multiplied by 4. Multiply those two numbers to give you an overall numerator over there. $19.62? Good, because this is double gravity. The denominator is still v squared times, what's cos 32, and then square it. Find out cos 32, hit enter, and then square that answer. What's cos 32 squared? What's cos 32 squared? Ant.
0.7225.
Okay, so I'm literally solving an algebraic expression now. Subtract the 1.25 over. We can do it. Subtract the 1.25 over. When I do that, I get negative 0.75 equals negative 19.62 over v squared 0.7225. Remember what we talked about with flipping them? You can switch v squared with the negative 0.75.
Just the v squared and keep the...
Yep. You could switch the v squared with the negative 0.75 and you can get your answer.
Then you square root it. The square.
Yep. And then you can get an answer by taking the square root. There's one more example. Okay? There's definitely an answer. I'll take a look. What I recommend you do tonight is watch example 5. We don't need for... Do we need for that tomorrow?
Yeah.
We do, actually, yeah. Tomorrow we're reviewing for the test. I think that's what we're doing in this one. Is that right? Okay, so look at the example 5 from section 3.3 on live video. Look at example 5 and work on the homework for 3.3. It's not an easy homework. That's why I told you to get ahead and start over the weekend. So if it takes you an hour, that's not unreasonable tonight. It might take you a solid hour.